Thanks very much for coming. My name is Tomas Petricek, and I'm talking about a paper called Data Exploration Through Dot-Driven Development. And this is part of a sort of bigger project that tries to make programming with data easier, and especially in context of media. So the idea is, if you're a journalist and you want to produce something like this, how can we make it easier for you to write the code or to transform the data into the format that lets you build some interesting visualizations? In this example, so this is a visualization that the New York Times team did that looks at the history of Olympic Games. So over time, you get to see what were the countries with the largest number of gold medals or medals overall. It's really nice. It's a really nice piece of work. You can find it on the New York Times. And when you come to it as a programming languages person, you're obviously thinking, well, how can I see what exactly they did? And even in something this simple, there's actually interesting problems because, for example, how you count medals for things like football, where there's 13 people getting medal in the end. Do you count it as 13 or do you count it as just one? So that's an example of an interesting decision that they had to make when building the visualization. And the idea behind this whole project is, can we do it so that there's some view source button where you can actually easily find how it was done and maybe change it to see the alternative perspective. So here, the way people like data journalists who built these visualizations work is there's these two options. For most people, it's really mainly Excel and using spreadsheets, but spreadsheets have a number of problems. They're error-prone. So there's a famous economics paper where they did off-by-one error when calculating some sums of columns, and as a result, they got the wrong numbers. It's also not reproducible because when you're working with a spreadsheet, you're actually modifying the data. So there's no like reproducible trace of what you've done. But the nice thing is that everyone can use spreadsheets. Now with programming, if you have a script that scrapes the data from somewhere, does the transformation, produces the visualization, then it's fully reproducible. Anyone can run it. It can also be analyzed. So you could imagine having various tools that will look at the sort of scripts behind various media stories and tell you what are all the data sources for it, doing some program analysis, is it using the units in the right way, and so on. But if you look at even the simplest programming languages like Python, there's actually quite a lot of non-trivial problems or non-trivial tasks. So this is an example in Python where I want to count, I want to sort athletes based on the number of gold medals they got from Rio, from the recent Olympics. And so I read a CSV file. The second line is doing filtering. So this is looking at where the column games is Rio. The input file is just a flat CSV with every single medal per line. So here I only get lines where the medal is from Rio. Then I group it by athlete and I aggregate where I sum the number of gold medals. And here you can see another syntactic construct because I had to create a dictionary. And then I sort it by gold and take the first 8. So even in this very, very simple aggregation, very, very simple script, I had to do quite a lot of different things. I had to understand what are dictionaries in Python to construct the aggregation. I had to figure out that the sorting, the filtering at the beginning, this is some sort of generalized indexer where it's parameterized by a Boolean and then it does a fancy lookup. You have to remember all the operation names because in sort of dynamic languages like Python, you don't really get very good IntelliSense or autocompletion. You have to know what the column names are in my CSV. So can we make this a bit easier? And that's exactly what we're trying to do with this paper. So I'll show you a quick demo that does the same thing. and I'll show it live. So if it goes wrong, we will see. And I've got Olympics as my preloaded data set. And then the nice thing is that when I type dot, it will give me an offer of the available transformations. So I wanted to filter data where game is Rio. And as I'm doing it, I get autocomplete that's offering me all the available options. So this is my filtering. Then I wanted to do grouping by athlete. And here as the next step, this is actually offering me all the possible aggregations that I can do over the data set. So one of those was sum the number of gold medals. And then I can sort the data. And as you can see, this is actually tracking the available columns throughout the transformation. So it knows that I have my key, which is the athlete, and the aggregated gold number. So I'll sort it by gold, and then take the first 8. And now I'll save this as a variable, and I can create a table to sort the data. And if I update the page, then something goes wrong. The thing that goes wrong is that I didn't, at the very end, I'm still in the transformation mode. So I need to say, get the data to actually get all the results as a data table. And then when I run it, I'll get a table with the Olympic medalists from Rio and their number of gold medals. So this was a simple example of the programming language or the system that we've been working on that lets you do data exploration basically just by typing dot and choosing one of the available members. And I think there's really interesting space in this data exploration. So this is a chart or an illustration from a talk by Jonathan Edwards, where he's been looking at end-user programming of social applications, but I think it's equally applicable in data science, where if you look at the spectrum of the available tools, the height is how many people can use it, and the other axis is how difficult it is. And there's this peak with spreadsheets, which are, a lot of people can use it, but it can solve only fairly simple problems. And then programming can solve, or is pretty complex, and can be used by a very small number of people. And there's this gap in the middle where there's sort of lots of problems that we could solve quite easily, but don't quite fit for spreadsheets and are just too hard for programming. So that's the space I'm trying to fill with this project. And I think that the key idea of the paper is that we can actually do quite a lot with this very simple approach of providing members of some object and letting people choose which of the members they want. So encoding fairly complex logic via a really simple mechanism of choosing a member of some provided object. And the way it works behind the scenes is that the language I was writing is very simple, nominally typed and statically typed programming language that has support for type providers. And type providers are a mechanism that lets you generate the types of the objects behind the scenes. So behind the scenes, there's some code that generates what will be the available members, and that's just a normal type that the programming language can then use and type check when you access members. One important thing here is that this is done lazily. So if you look at the types that I was working with in the example, there's really quite a lot of members. If you type dot, it will generate the next level, and then you can sort of explore further. But if you wanted to generate source code with all those types, it would be potentially infinite. So you can't really code gen the whole thing. And the type providers work lazily. So as you look as the type checker explores parts of the program, it will evaluate and sort of get precise definitions of the types it needs along the way. The other interesting thing is that this actually lets us encode many of the fancy types that people in the programming language community have been working on in a sort of very user-friendly and simple way. And I'll have a concrete example of this shortly. So more specifically, the part that is presented in the paper is this pivot type provider. The idea of type providers in this context is that you define some sort of mapping or type context that maps names to definitions and more nested types. So L, you can see it as a function that takes the type name or class name. It gives you the definition of the type, which is some type with some constructors, some members. And then it gives you some more types that might have been generated along the way. And then the pivot, the concrete type provider, like the one that lets me do this aggregation and so on, can be parameterized by something like a schema of the CSV file, which was the case in this example. And then it gives me the top-level type, the top-level class, together with all these nested contexts that the type checker can then explore as needed. So a concrete example, and I'm not going to go into a lot of details here, but a concrete example is the top-level class. So when I typed Olympics dot, it came with these and a few more options. And so the way this is constructed is that I'm really just defining a function that when I give it the names of the available columns in the CSV file, it will generate type where some of the members, or all of the members in this case, return some other type that's generated by some other function that sort of looks specifically at the available fields or columns in the data source, and based on this, it will generate type specifically for CSV files with this structure that let you do the transformations, sorting, and so on. So this is the mechanism behind the scenes that's generating the type as you're writing the code. And I think at this point, I'd like to just go back to this a little bit and say a few more things about how this works. So I'll start from scratch. And the interesting thing here is if you look at the Olympics data set, then one of the operations here is drop columns. And this is a very straightforward one where it just goes through all the available columns in the CSV file and it generates drop and that name for every single one. And the nice thing here is that this is actually, or you can see it as encoding fairly complicated logic or fairly complicated type system mechanism. So here, if I say drop discipline, and I say drop, let's drop, I don't know, sport, let's drop event, let's drop games. As I'm doing it, the columns I dropped are actually disappearing from the list. And that's because of the way the types are generated, but it's also, you can see it as encoding of various work on row types in the type theory world. So if you were doing this in some other programming language, you could say, well, let's just encode this dropping or the typing operation of this dropping using row types. So here, the rule is saying if I have an expression E, which has a type that contains F1 to Fn fields and n different fields with n different types, and if I write drop Fi, then I'll end up with a type that contains all the fields except for the Fi field. And this is what some programming languages with more powerful type systems let you do. And the way we can do something that's very much similar without a very complex type system is that we can say, if I have expression E with type C1, then E drop Fi is going to have type C2, and drop Fi is just a regular member of the object. And then on the side, I can keep some relation, which is what the paper uses, behind the types and the fields that actually exist in the type. So this is this ends up encoding very similar principles, very similar structures, but rather than using very fancy type system, we can do this with just simple nominal typing and members. And this is really nice idea. And in this paper, we do this with, or we encode things that you could otherwise track with row types and phantom types. There's some other work that people have been doing on encoding session types using type providers. And I think there's potential for adding a lot more other interesting things, interesting work that has been done on type systems, encoding it in this very simple, user-friendly way. And the last thing I wanted to show, so this is going sort of further than just looking at the type systems and the type theory or the formalization of how the type providers work, because what I said earlier was this sort of mismatch between spreadsheets and programming languages. So here, the idea was, now that we've simplified the language to just do dots and so on, can we actually sort of take the next step and make it a bit more like working with spreadsheets? And so this is the same code I was showing before, but now it's running with another feature turned on, which lets me, whenever I click somewhere in the code, it generates a preview. So if I go here and say, let me do dropping again, I can drop columns. So if I don't care about the event, I'll drop it. And now you can see in my table, event isn't there. I could drop something else. So let's also drop discipline. And if you look at the preview, again, you can sort of explore the data as it looked at different stages. So you load this again. The other interesting thing, so here, if we say filter by RIA, and then group data and do sum, the editor tries to go a bit sort of further than just giving you a preview. So what I can do as well is, based on the available members, we are automatically providing the UI that lets you add the different members. So at this point, when I'm in a group by and I group the data by athlete and I sum the number of gold medals, maybe I also want to count all the different medals. So I'm going to do that. And now you can see the number of gold medals and also the new column. And I can go to sorting. And rather than sorting it by the number of gold medals, I can change it and sort the data by the number of all medals. And then if I go back to my preview, this will be showing the number of all the medals. So the idea here is sort of to explore where you can go if you wanted to bridge the spreadsheet world and the programming languages world. And the editor that I was showing here relies quite heavily on the very simple structure of the program. So as it as it generates the editor, it will just look at all the members that have been generated or used along the way. All the sort of add a new operation is, again, looking at the available members of the provided type and so on. So this is all I wanted to show. I think the summary of the talk, there's really three interesting things. One is that I think, especially in programming tools for data science, there's really sort of interesting space between the very simple and not reproducible and error-prone spreadsheets and the programming languages that are really hard to use for many, many people who would otherwise be interested in exploring data. The key contribution of the paper is that if you take this dot-driven, as we call it, dot-driven approach, you can actually express quite a lot of non-trivial operations such as aggregation, sorting, transformations, using a programming language that pretty much has just the member access. And this is also an interesting way of encoding work that's been done in more fancy type systems into a language that's really, really simple. And if you have any questions, there's contact details here. You can learn more about the work at dgamma.net, which has the editor that I was showing, so you can play with it. And the paper is available on my website. Thank you.
So can you put Skype on? Thank you. Thomas, can you hear us? Do we run it from here? Hi, Thomas, can you hear us? Right, so we just heard your YouTube presentation. We heard and watched it. And we also clapped and thanked you, but you were not there to hear that. And now I invite the audience if they have any comments or questions.
So I was wondering, for those row types that you mentioned, it seems that you are doing runtime checking such that you would never need to abstract over them. You never need to have something like a constraint that certain two row types must be disjoint or other things that are associated with not knowing what's in the row. Isn't it true you know that?
As in some other environments. And so here what we are doing with the row types is that we infer some information about the data source from the actual values from the data. And currently it's just inferring what kind of columns are there, and what are their types, and the types are just primitive types like string and number. But we could definitely infer more information from the data source, such as whether there's missing values or not, and then give the user some option for handling the missing data.
Yeah,
Did that answer the question?
Yeah, I think so. I'm tempted to conclude that you're solving a problem which is not so hard because you do not cover a lot of cases that could arise at runtime, because you are actually looking at a particular situation, and that means you can act directly on what the situation is.
So I think it can get a bit more interesting if you wanted to do the inference based just on a sample of the data. And that's something we've been doing in the type provider's work in F#. And I think that's something that will probably come up here as well eventually. So for example, if your data source was something of several gigabytes where you can't really initially in the first phase iterate over it, then we'd have to take some sample and make our best guesses about the type based on the sort of subset of the full data set, and then it will have to include some sort of runtime handling where the values we might get at runtime don't actually fit the inferred type from the compile time.
Hello. I couldn't follow a lot of the details of your presentation because of the resolution of the YouTube video. But it looked very much like what I've seen type providers do in F#, which is pretty impressive and a great teaching tool. But can you summarize the differences between what F# has done and what you're doing here?
Yes. So F# has the general type provider mechanism, and what I'm doing here is sort of implementing one specific type provider. And what's new and interesting about the type provider that I was presenting here is that most of the F# type providers sort of let you access data by slicing some file or some database and navigating through it and finding one bit of data that you want to get. What's new and interesting here is that the type provider provides types for constructing a more complicated query. So here, the type provider, behind the scenes, it doesn't just slice the data, but instead it lets you build up this relational algebra-like query to group the data, filter the data, sort the data, aggregate the data, and so on. So the new thing here is that we're using the type provider not just for sort of slicing the data, but for constructing a query or constructing a more complicated program or script that lets you do something with the data.
So you can use it on the results of another filter, and then you can use it again at the next step.
Yeah, that would be the idea. So you could, one of the things I've been looking recently is getting data from HTML from web pages. So if you want to get data from Wikipedia, for example, you could have one type provider that lets you sort of find the appropriate table in a Wikipedia page, and then use this work to let the user count events in January 2017 based on something, for example.
Thank you.
No further questions, and therefore we will wish you all the best for the baby, and we will thank you again.